can slowly get started. So welcome everyone to this talk about Akka Streams in Java 8. I used to give this talk in Scala, and I've never seen so many people attend, so perhaps it was a good idea to convert it into Java 8. My name is Jacek Kunicki. I work at Software Mill. We are a 100% remote and flat software house based all around Poland. So if after this talk you would like to talk about either Akka Streams or remote work, please feel free to catch me somehow. So if you attended the State of Akka talk on Wednesday, you may already have heard that there is a Java API for Akka. And the people usually, when they think of Akka, think, well, it's a Scala library. It is written in Scala, but there are Java APIs as well. So let's see today how much they are worth. So to introduce the topic of stream processing, let's see what it generally looks like. I think most of you are more or less aware of it, but this is just a quick recap. So we have some source of our data. We can, in general terms, call it a producer. We have some endpoint for our data, which we can call a consumer. And then we have a number of processing stages. So we want to do something with our data. And the usual flow of data is from the source through the processing stages and up to the consumer. Akka Streams, which is an implementation of the Reactive Streams manifesto, adds something more, and it's actually Reactive Streams that adds something more. Because in a stream processing pipeline, you can basically imagine two scenarios. The first scenario is when you have a slow producer and a fast consumer. And this is actually no problem because, well, the producer is producing data kind of in a very slow manner. The consumer is fast, so there is never a danger that something wrong happens. For example, the consumer gets too much data. But you can imagine the opposite scenario where you have a very fast producer and a slow consumer. And then, well, it's kind of problematic because you need to find a way to deal with the amount of data the consumer is getting. And there are a number of ways to do it. For example, on the hardware level, you can just drop packets or drop the data. And in the Reactive Streams concept, this is solved by something called backpressure. So there is another kind of data flowing, let's say, in the opposite direction of the stream. And backpressure is basically about the consumer signaling the producer how much data it can consume. So basically, the producer can never send more data than the consumer has actually requested. And this is a kind of a simple way to guarantee that the consumer is never flooded with data. So this is the main difference between like normal, let's say, stream processing and the Reactive Streams approach. So this is like the general terminology for stream processing, and in Akka Streams, the idea is similar, but the names are different. The producer is called the source, the consumer is called the sink, so this is the very end. Then we have the intermediate stages, which we can call flows, and the source, sink, and flows form a graph. Actually, the graph is the graph is also a flow. So like the terminology is not that simple. This is a simplification here. But in terms of the API we will be using, we have a source, we'll have a sink, and we will have flows that are the intermediate stages of processing. So there is really a lot of stream processing libraries. This is a slide from my colleagues' talk about small intro to big data, and you can see a lot of stream processing frameworks here. Akka Streams is not among them, I think, so you can see that there is a lot more to it. So you may ask yourselves how Akka Streams are different. So first of all, Akka Streams are not distributed. So compared to Spark Streaming, for example, Spark is usually run in a distributed manner on a cluster. Akka Streams is not distributed. This is actually not entirely true because like last year there was an initiative in an Apache Gear Pump project to create a materializer. So I'll explain the materializers later, but a materializer is basically a way to run a graph defined in Akka Streams. And actually the guys at Apache Gear Pump attempted to write another materializer, and Apache Gear Pump itself is distributed. So this could be a way to run Akka Streams in a distributed fashion. When writing Akka Streams code, you basically define some reusable building blocks. So you define small pieces which tell how to process the data. Then you build something bigger from them. And it's very important that that the building blocks that you are writing are lazy. So nothing actually happens. No data is processed until you explicitly tell the Akka Streams to run everything. So this is an explicit step that you have to execute to run all the processing. Until you do it, all the definitions of the building blocks are lazy. So those are just recipes for processing your data, and nothing really happens. So our use case, this is actually a simplified version of a project we actually did with Akka Streams, will be about importing data from CSV files to Cassandra, which, well, is just a random choice here, actually. We used it in the project, so it's here in this talk. For this amount of data, we could use any database, but we have Cassandra. And we're going to do some intermediate aggregation. In the middle, we'll be averaging the readings. So our data looks like there are values which can have there are like entries that can have an ID, and they can have a value. For each ID, there are going to be 2 lines in every file. And any of those lines can be a valid value or an invalid one. So you can see an example of 2 valid lines at the beginning, then you have 1 invalid, 1 valid. It can happen that both are invalid. And what we are going to do is to average those lines by ID. So for every ID, we're going to compute the average of the lines. If both are invalid, we're going to use some dummy value just to store it in the database. And the files there are semicolon separated values, but we'll also gzip them. So like our input are gzipped CSV or semicolon separated values. Then we're averaging them and then putting them into Cassandra. Okay, so this is a live coding talk, so that's the end of the slides. There is one credit that goes to my colleague Maciek Opała, who helped me with converting the code I wrote in Java 8 to use waiver or Java slang. Until recently. So thanks, Maciek. The code would be nicer thanks to this contribution. Okay, so we're going to start. Well, here we have some boilerplate. This is just a simple class for our CSV import. There is some configuration. I will explain the parameters when I actually use them. So let's just assume they are there. So the first step we're going to write is so far not related to Akka Streams. We're going to prepare a recipe for parsing a line. So we have a line as semicolon separated values, and we want to convert it to our domain model somehow. And it's important that in Akka Streams, actually all the processing we're doing is asynchronous, so we'll be dealing with completion stages, with completable futures here. So we're trying to do everything in an asynchronous manner. So here our method for parsing the line is going to return a completion stage of a reading. Now, what's a reading? Reading is a part of our domain model, and basically this is an interface that provides an ID. We have a valid reading that, as I explained, apart from the ID, it has a value. And we also have a domain representation of an invalid reading that just has an ID to make things simpler. So we're going to return a completion stage of reading. We're going to call the method, well, parse line, because we'll be parsing lines. And what will arrive here is just a line. Okay, so since it's going to be asynchronous, we start with creating a completable future to make the computation asynchronous. Future. We have the supply async method, which basically lets us execute any code asynchronously. And now we're starting with splitting the line by the semicolon, so by our separator. And we're going to call it fields. Now, first we're going to extract the ID. So we're going to take the first value, the first field, 0 actually, and we're going to call it ID. Then in a similar fashion, we're going to extract the value that is going to be a double. And this is our value. Well, and in the happy path, we could just return a valid reading with the ID and the value. But this is actually the happy path. We need to remember that we can have some invalid values as well. Oh, and we need a return here. So we're going to, this is the first place where we are going to use waiver and the monadic try instead of just writing a try-catch clause. So what we are going to do, well, we'll still be using the value here. And we're going to say that we want to return a try, and this is the waiver try of. Now we provide the function that we want to actually try executing. So we're trying to extract the value. Then we're going to use the extracted value to create a valid reading if everything goes fine. So we map the value to a new valid reading of an ID and a value. Then we want to introduce some error handling that, well, that we just know when something goes wrong. So basically there is the on failure part, and we can have an exception, and we can just log it to know what's happening. And in case of failure, we want to get an instance of an invalid reading instead of a valid one. And invalid reading just has an ID. This still doesn't compile because actually the return type of the try is determined by the type of the value that is within the off clause. So since we are returning either valid or invalid readings, we need to cast it to, sorry, not here. Here, we need to put the cast to reading here, and then it should know that, yeah, that the value is of the proper type. And sorry, but I'm a Scala developer, so I'm forgetting the returns and semicolons. I try to do my best. Okay, so this is the first part that, as I said, had nothing to do with Akka Streams so far, but now we're starting to do with Akka Streams actually. So the next step is, well, when parsing our files, when processing our files, of course, we won't load the entire files into memory because that's not going to be efficient. Actually, what we're gonna do is stream the files using the built-in Akka Streams components. And when we stream the files, we're basically receiving streams of bytes. So if you want to split the streams of bytes into lines, we need to somehow use the new line separator, new line character, to just like split the stream somehow. So the next method will use the built-in Akka Stream stages, and it will be used for delimiting the stream of bytes. And this is going to be defined as a flow. Now a flow is one of the classes in the Akka Streams API, and it has 3 type parameters. The first parameter is the type of the values that get inside. The out type is the type of the values that get outside, and the third one is the type of something called the materialized value. And basically, if you think of a flow, so a part of the processing graph, all the data that is getting inside and getting outside and communicating with other parts of the stream is a stream as well. So this is like internal to Akka Streams, and the flow of data between different parts of the graph is realized in a streaming manner. But it's also possible to emit a value to the outside world from a flow, for example. And materialized value is actually the thing that you can emit to the outside world from a stream. So in our case, we almost won't be using the materialized values. So we'll just be playing with the input and output types, because well, we don't need it in this case. So our delimiting flow would work with type called byte string. And it's basically a stream of bytes, so it's some Akka a type from Akka that is an abstraction from a stream of bytes. So we're going to take a stream of bytes, then we would like to delimit it by new line characters, and we're also going to emit a stream of bytes. Then we'll convert it to a string. But the emitted streams of bytes would represent the actual lines. So our input type is going to be the byte string, the output type is going to be the byte string, and the materialized type is going to be something called not used. And not used is basically a compromise between the Scala and Java APIs, because in Java you have the void type, the like capital V void. In Scala you have unit, and since the authors of Akka wanted the API to be unified between Scala and Java, they decided to introduce some types that like tie together voids, units, and like the Java word and the Scala word. So not used is basically something. In the Java word you can think of it as void. In Scala you can think of it as unit. But it basically says that we don't care about the value. So we call the flow line delimiter. And here we'll be using some built-in components. So we have a component called framing and a delimiter method here. which basically needs a byte string as the delimiter. So we basically give the new line character here. Then we need to define the maximum length of the line that we want to process. Well, our lines are pretty short, so I'll use 128 as a reasonable value. Then we have a third parameter that's called framing truncation. And this basically says what should we do if we get a stream of bytes that doesn't end with the delimiter. So you may imagine that in your files, the last line doesn't have a new line character, so you don't have the new line character at the end. And the default behavior of the delimiter is that it would fail if it doesn't encounter a delimiter. We don't want it to fail. We want it to use a line without the new line character as a valid line as well. So we'll say that we're going to allow the truncation. So we're going to say framing truncation allow. The default value is will not allow, and it would make it fail when for any reason there is no new line character. So this is the first flow that we defined in terms of the Akka Streams API. So far we didn't write much on our own because we're using the building stages. But now the next step we'll use some more of our input. So the next step is going to parse. We are going to parse a file, and so when parsing a file, we'll also define a flow, because as you will notice, like all the building blocks that we are defining are of type flow here. The input type of the flow is going to be a file from Java.io. The output type is going to be a reading. So far it can be either a valid one or an invalid one. So it's just a reading. We use the interface here. And well, the materialized value, we don't use it, so we just don't care. And we're going to call it parse file. So now when we want to define like our own flow, we start with also with the flow class. And there is a static method called auth, where we can like define the type that we'll be processing, so like the compiler doesn't complain. Here we're going to have a flow that is going to process files. So we have flow of file.class. And then we want to do something with it. And what we'll be doing here, I'll just write the method name here, flatmap concat. I'm going to explain it in a moment, so don't be scared, because I'd like to write the actual implementation. Then it would be easier to understand what flatmap concat actually does. The important thing so far is that it will give us a file. So basically, we're writing a flow that processes files. So in the methods that we are calling, we're going to get the instance of the file, and the flatmap concat will be called, say, file after file. So we're going to have an instance of the file here. And what we are going to do? Well, you remember that the files are gzipped. So we're going to use a gzip input stream, which will be wrapping a plain file input stream created from the file that we got here. We're going to call it an input stream. And now we use some built-in thing from Akka Streams that is called stream converters. And it basically lets us convert an input stream. So we have a, let's see the signature actually. So basically we provide an input stream, or actually a function that creates an input stream. And what we get as a result is a source of byte strings. So source, as you remember from the first slide, is the initial part of the processing graph. And the stream converter basically takes an input stream and converts it into, brings it into the Akka Streams world. So it converts it to a source. And from the source, we are emitting byte string. And now let's explain what the flatmap concat method actually does. So here, for every file, we are going to create a source. So we'll end up having like multiple sources emitted. And actually, we don't want multiple sources emitted from the parse file flow. We want a single source, which will be the source generated inside, concatenated. And that's what the flatmap concat method does. It actually takes a source of sources and flattens it into a single source by concatenating it. So that's, I hope this explains it a bit. If not, you can, actually, the entire code is available on GitHub, so you don't have to take notes, at least regarding the code. So you can just have a look at it later, try to run it, or just ask questions. So here, as I said, the from input stream method needs a function that returns an input stream. And now the next thing we are going to do is use the via combinator, and the via combinator says that we are going to, like, the value that is emitted by the source is going to go via another processing stage. And here the processing stage is the line delimiter. The next thing we are going to do, we are going to optionally drop a number of lines, because, well, you can imagine that you can either have a header line in the CSV file or not, so you may want to drop it. This is a configuration parameter that says that you can drop as many lines as you want from the input. And now you remember that our source emits lines, but it emits lines in forms of byte strings. And actually our parseLine method that we defined at the beginning needs a string, not a byte string. So we use the map, not map async, map stage to map the byte string to a normal Java string. So we take byte string, and the method is called UTF-8 string. Yep, and well, this is like when writing Scala and using IntelliJ, the IntelliJ is really slow because the Scala plugin is, well, it's the best from the things you can have, but it's still not performant. I thought that in the Java world it's better, but here is a place that it actually slows down IntelliJ tremendously. I don't know why it is, but this part when I'm mapping that, when I'm using the UTF-8 string, somehow is almost able to kill IntelliJ. So I really don't know why is that. And I actually need to, well, write it without the syntax completion and stuff like that. So we have our line converted to a string, and then we want to convert it to a reading, because the output type of our flow is the reading. So that's what we want to get out. So we have a string, we want a reading. That's great because we have the parseLine method that converts a line into a reading, and it does it asynchronously because the parseLine method returns a completion stage. So now we can use the map-async method. And map-async takes two parameters. First of them is the parallelism. So it basically says how much parallel executions of the code you want to have. So in our case, we have a configuration parameter called non-IO parallelism. And this is like some arbitrary value used for all that we're going to use for the computations that don't require IO. So no database, no reading from files. And here we just pass the reference to the parseLine method. We need a semicolon, we need a return here. Yep, and let's wait until it tries to compile it, and we'll see just later how it works. Okay, so this is this is the method that will take a file and convert a file into a source of readings, because the return type of the entire thing here . Well, okay, it won't say what it is, but it's basically a source of strings. So we have a not source of strings, source of readings. So of our domain model. Okay, it actually managed to compile it, so it looks everything is fine now. So the next step after so far we know how to delimit our stream of bytes into lines, how to parse a single line to our domain model, and actually how to parse a entire file into a source of our domain model objects, so the readings. So the next step is the aggregation I was talking about. So what we want to do here is having the stream of readings. We want to group them in groups of 2, because, well, here we're keeping the order. I will explain it in a second as well. But the readings are still in order, resembling the order in the file, so we can just group them by 2, then and we will have pairs of readings with the same ID, and then we can try to average them. So the next flow is going to take a reading, and it's going to return a valid reading, because the output of computing the average will always be a valid reading, because we want some value to store in the database. And as I said, if it happens that we have in the pair of readings we have a single valid one, we'll just return the value. If we have both invalid readings, we return some arbitrary value of -1, just to have a kind of default. And the materialized type is still not used because we don't care, we don't emit anything to the outside world. So this is going to be called compute average. And now, once again, we're using the flow, the static off method in the flow class. Here we provide the type of the values we're going to process. Now we're going to group the readings in groups of 2. And then we want to asynchronously average them. Now you can see that there are 2 variants of the map async method. The first is the one we used in the previous in the previous section where we were parsing the files, and there is a second one called map async unordered. And the difference is that map async executes the code like the given code asynchronously in a number of parallel executors, but it keeps track of the order in which the elements arrived and emits the asynchronously computed values in the same order. But if you don't care about and this was important when we were parsing the files because we wanted to emit the readings so the same IDs are next to each other. So we cared about the order. Here, when averaging the readings, we actually don't care about the order because we already processed the groups, and it really doesn't matter in what order we emit the average readings. So we can use the map async unordered variant here, which is certainly faster. But it can break the order, so it depends on your use case whether you want to keep the order. Then use map async, which can be slower because it needs to wait for the computations before it can emit downstream. If you don't care about the order, you can use map async unordered, which would be faster and will just emit a value downstream as soon as it's computed, not waiting for the other values that are possibly dependent. So we use. Okay, yeah, we're back. Great. So we are using map async unordered because we don't care about the order of the emitted values. So we're using the non-IO parallelism once again because this is a non-IO operation. And what we're going to get inside our flow is a sequence of readings. It will always be 2 readings. So actually it's a group of 2. And now what we are going to do, since the method is still map async, so we need to provide an async result. So once again, we're going to use the completable future supply async to do the computation. And the first thing we want to do here is we need to filter the readings to only extract the valid ones. So our approach will be to extract the valid readings, and then having if we have a non-empty list of valid readings, we're going to just average them. In some cases, we'll be averaging a single reading, but well, it's not about performance here. It's just about simplicity of the code we're writing inside. And if the list of valid readings is empty, then we'll just return the default value of -1. So here's the next place I'm going to use waiver. So I'm going to use a list from waiver, which basically has better capabilities of the streaming behavior. So you don't have to write stream and then collect to something every time. So I can take the readings. I can filter them using the isInstance method from the valid reading class. And then, well, it would filter the readings, but the type would still of the output collection would still be reading. So what we need to do is map actually cast the readings to valid reading. So this would give us a list of valid readings, and the type would be a list of valid readings. So that's what we actually want. Now the next step is computing the average. So we take the valid readings. We map them to the value so that we have a stream of doubles. And then the waiver gives us an average method on here, so we don't need to use a collector, we just say average. And actually average in waiver returns an option, and the option is defined when the list was non-empty. And if the list was empty, the option is not defined. So this is a perfect case for us because we can just call get or else here. And if the list was empty, we can, so there was no valid readings, we can just return our default value of -1. And this is going to be our average. Now what we need to do is to return a valid reading. So now we need the ID, but we had a group of 2 readings, and even when the reading is invalid, we have an ID, and that's why we actually defined our domain model with 2 classes, a valid reading and an invalid one, because here, even if both of the readings were invalid, we can still take the first reading from the collection and take the ID from here. So we can say readings get 0 and just get ID here, and as the value, we're returning the computed average. Okay, and we need a return here, of course. So this was the step for computing the average of 2 readings. So once again, first of all we filtered the list to extract only the valid readings and to map them to a proper type. And then for each group of valid readings, we just averaged them or took the default value when the list of valid readings was empty. Now the next step. In the next step, we're going to see how to combine the building blocks that we defined so far to form a bigger flow. Because a flow, as you have seen so far, takes an input type, an output type, and actually you can define the flows as small building blocks, but you can as well combine them. We actually saw it when we were using the via combinator. So now we're going to use it once again. And now we're going to define a flow for processing a single file. And processing a single file will take a file as an input, and it's going to return a valid reading, because this would the process single file step would combine the file processing and the average computation. The materialized value is still not used. We're going to call it process single file. And it's going to return a flow of file class, and then we're just calling via parse file. So we're using the first building block that we defined, which converts files into readings, and then the second stage that we are going to use is computing the average. So combining the building blocks that you defined previously is as simple as that. So you define a new flow, and then you just use the via combinator to add subsequent processing stages. So that's all you have to do to combine them. And the last thing that we need to do with our valid readings and the average ones is store them to the database. Now, so far we have defined flows, so components that have an input and have an output. Now, storing to the database actually doesn't need an output, because the output is the database. So we're going to use something else, not a flow. And what we are going to use is a sink. So as you remember from the first slide, sink is the last stage of the processing graph. And the difference between a sink and a flow is that a flow has an input and an output, but a sink only has an input. So we're going to define a sink. Well, you can see that the sink has less type parameters because it only has an input and a materialized value. And actually, we're going to use the materialized value here. I'll explain later why. And the input type of the sink will be a valid reading. And after we store the readings into the database, this will be executed also asynchronously, and we want to be able to wait for it. So wait until the entire sink is complete. So until all the elements have been inserted into a database. So now, so the materialized value of our sink, so the value that is going to emit in the to the outside world, would be a completion stage here, because it would be executed as a future, and we want a completion stage as an output, so that we can wait for it, basically. So we're using a completion stage which needs a type parameter, and I told you about the differences between the Java and Scala API. In Java you have voids, in Scala you have units. So we had the not used materialized value before, and here we have another value that ties Java and Scala together, which is called done. And it's basically also a void or a unit, but the meaning of it is that we don't care about the value that is actually emitted from the sink in this case, but we just care about the fact that it has completed. So that's why it's called done. It's going to be called store readings. And what we do here, we'll start with a flow. So when if we start with a flow which has an output, we would somehow need to deal with that output because ultimately we want to return a sink, not a flow. But let's start with a flow of valid reading. And now we want to asynchronously store it into the database. So we're once again using map pacing unordered because we really don't care about the order in which the readings are stored in the database. Here we have a different parameter for the parallelism because this is an I/O operation storing to the database, so we may need to separate the configuration. And we have something called the reading repository. It really doesn't matter what that is in details. You just need to know that you have a safe method which takes a valid reading as a parameter and returns a completion stage. Here of a result set. This is a result set from the Cassandra driver. We actually don't care about it because, as I said, for the sake of simplicity here, we just want to know that the inserting was completed. We just ignore the result sets here. So this is the signature of the safe method, and that's all we need to know here. Now we want to actually extract the materialized value, because in this case we're interested in the materialized value. And to extract the materialized value, we have a toMat method, which takes a sink. Like all the methods that start with to take a sink. And that toMat version takes a sink and returns the materialized value from the sink. And now we're going to use a built-in sink called ignore, which basically says that we are ignoring the return type, so we're ignoring the result set that comes from the safe method. But we are just interested in the fact that it has been completed. So we're ignoring it, and you can see in the signature that I'll show it actually, that the ignore sync returns a completion stage of done. So that's why our return type is the completion stage of done. And there's one more thing we need to do here, because basically if we are fusing, we're taking our flow, we're taking a sync, and we are like connecting them together. And then we want to take a materialized value. And now we want to decide which materialized value we're actually interested in. So we can either have a flow, which is, well, from your perspective, it will be on the left. So on the left we have a flow, and on the right we have a sink. And we're interested in the materialized value from the sink, so from here, not from the flow. That's why we have a combinator here called keep. And it basically lets us choose which materialized value do we want. We could ignore the value, we can take one of them, we can take both of them. In our case, on the left-hand side we had a flow, on the right-hand side we had a sink, and we're interested in the value from the sink, so we'll say keep right here. And basically like fuses the flow and the sink together and takes the materialized value from the sink, so from here. And that's why we're using keep right. If we chose keep left, it would take the materialized value from the flow instead. Okay, so far we have defined like all of the building blocks that we actually needed for processing our files. So now what we have to do, what's remaining, is just to like put them all together to process our files. So we're going to have a method that returns a completion stage of done, because this is the return type of our like entire processing pipeline. Oh, sorry. It's going to be called import from files. Well, there's a number of things we're going to do here. Well, first of all, we're going to list the files that we actually want to import. So we have a configuration parameter called import directory. That's a file. So we just use the list files. And we are still using the waiver list. So the list of method comes from the waiver list, not from the Java util list. So those are our files. Now let's do some logging that we just know what's happening. Let's log the start time so we can measure how well it behaves. And now what we're going to return here is now we basically want to combine all the building blocks that we defined before and actually run them. So, well, if you remember from the first slide, every processing graph starts with a source. So we're also going to start with a source, and our source will be the collection of files. So now there is a source from factory method that takes an iterable and converts it into, and like brings the iterable into the world of Akka Streams. So it converts it into a source. Now we're going to like pipe it through our process single file stage. So the one that takes a file and produces a valid reading. And now the last stage of our graph is actually like we need to define a sink, so the last element of the graph, and we want to run the graph. We could do it separately, so we could use a to method with a sink and then the run method to run it. But since you do it very often, there is a method that combines those two. So you just have the run with method to which you provide a sink. Or actually, if, as you see in the signature, you provide a graph that has a shape of a sink, because every graph in Akka Streams has a shape. It can have a shape of, for example, a source, a flow, or a sink, and some other shapes as well. So we're interested in the sink shape here. So we're going to use our sink here. That's called store readings. We'll also do some logging to like leverage the start time that we used and see how it went. And you can see that it still doesn't compile. It doesn't compile because, as I said previously, everything that we defined so far is lazy. So there is no actual processing. Nothing happens so far. And for something to actually happen, we need a materializer. And the materializer is basically something that turns the definition of a graph, so the graph we have, into something that can be run. And in Akka Streams, the default materializer that is used is based on Akka actors. So there is an actor system underneath, and all the recipe that we just created is converted. It's optimized. It's checked for like some issues, like if everything is connected correctly, and then it's actually run using the actor system somehow. So what we need to provide to this run with method is also a materializer. So we need to provide a way to actually run our recipe. And so default materializer is the actor one based, the one actor based. So we're just going to create it. And we already have an instance of an actor system because this is one of the dependencies of our class. So our materializer would be actor system based. So that's almost there. So now you can see that we define the source. We take the iterable of our files, bring it to the Akka Streams world, then we pipe it through the process single file, and then we store the readings. But please notice that in this case, we are processing like file by file. So for every file, we are converting it into a source of readings and then storing them. And actually, you could imagine that it would be better to process the files concurrently. So if you have a bigger number of files in the directory, you may want to basically load balance them between a set of among a set of workers. So you have some input point, you have a number of workers, you want to for every file you want to choose a different worker when it's available, and then like just merge the results together and emit the valid reading downstream. So we're going to create a custom graph stage for this load balancing. It's going to be called the balancer. And it's going to have a single static factory method. And it's going to be defined in some more generic ways. So it can be used here, but it can be used for any load balancing when you provide number of workers and the logic of a worker. So it's going to have two generic types, in and out. And it's going to return a graph. And a graph, as you remember from the previous signatures, has two type parameters. The first is the shape, and the second one is the materialized value. So in our case, our graph is going to have a flow shape, because we have an input and we have an output, and the load balancing is going to happen inside. So the flow shape, the flow is going to take the in type as an input, the out type as the output, and the materialized value is not used. So we still won't be caring about it. Now we call the method create, and we need two parameters. First parameter is the number of workers that we want to use for the load balancing. And we need an actual logic for the workers. So what we actually want to do with what work is going to be done by each of the workers. And each of the workers is going to be a flow with input type in, output type out, and the materialized value of not used, and it's going to be called a worker. So now we can use something that is called graph DSL, and it's basically a DSL for creating your own graph stages. So far we've been using the predefined ones, the one we have in Akka Streams, but we can also create our own. And basically, in the simplest case, like to create a custom graph, you need something called a builder, which basically lets you manipulate the structure of the graph. So you get an instance of the builder, and then you can add your own smaller stages to build your own graph. So the first stage we're going to add to our graph is called balance. And this is a built-in stage from Akka Streams that basically, well, it has an input type and an output type as well. And what it does, it takes the input and balances into a number of outputs that you define. So we're going to create the balance stage. And the number of outputs is going to be the number of workers, because we'll be taking like something at the input and splitting it among the number of workers. And this is going to be our balance stage. You can see that there is like some kind of type. It's called uniform fan-out shape. It's really not very important at the moment. The next stage we're going to use is the merge stage, because the balance stage like balances the load between workers, but then we want like for every wait for every worker to complete its job. So we want to have a stage that like collects the output of the jobs from all the workers and passes them downstream. So this is another built-in one. It's called merge. And it also needs to have the number of inputs set to number of workers. And actually, this won't be verified at compile time, but it's going to be verified at runtime. So if the number of, for example, if you leave some output not connected or input not connected, Akka Streams is going to complain at runtime. And now, well, theoretically, it could be enough to just return a flow shape, because we need a shape here of. And now the input of our flow, of the bigger building block, is going to be the input of the balance stage, so the one here. And the output is going to be the output of the merge stage, so the one here. But actually this is not enough, because we need to explicitly tell that we want to connect every output of the balance stage to the worker, and then we want to connect the output of the worker to the input of the merge stage. So, and we need to do it manually, so all the connections are there. If we don't do it, there will be runtime errors, because Akka Streams is going to, like the materializer is going to validate the graph definition, and it would see that something is wrong, that you have like dangling inputs or dangling outputs that are not connected anyway. So we'll take an in stream here. We'll iterate from 0 to the number of workers. And for each worker, basically, what we're going to do, there's another explicit step we need to do, because we need to use the builder to add our worker to the graph. So builder is the thing that manages the structure of the graph, and we need to explicitly call the builder to add the worker to the graph. Let's call it worker stage, for example. And now we actually want to connect the inputs and the outputs. So we take the builder. We say that it should start from the output of the balance stage, like an arbitrary one. So we take the balance, and we have an out method that chooses a particular output. So here we choose by the I index that we have. Then we want it to pipe it through the worker stage, and ultimately we want to like put it into the merge stage. So now we're going to choose one of the inputs or the merge stage. So we just say merge in of I. So now we connected like every output of the balance stage to a worker, and please notice that this is the same worker, so we don't create another instance of the worker. Like the workers are stateless. So we can share the instance. So we take the output of the balance, connect it to a worker, then take the output of the worker and connect it to the input of the merge. So that's what we are doing here. And this is our generic load balancer. And now, well, the last thing we need to do is have a kind of a main method that is going to run everything. And it's pretty simple. It basically loads the configuration using the typesafeconfig library, creates the actor system that will be needed to run everything, creates the reading repository, and then we just create an instance of our importer, run the import from files method that returns the completion stage, so it's part of the Scala concurrent. And then we have some shutdown routines to just like shut down the actor system and shut down the repository, so the Cassandra connection. So now we have a Cassandra running in a container. There is like an old version, so we're going to truncate the table. So now our table is empty. What we're going to do now is to run our importer. And you can see, like, the error messages you see are from the invalid lines. So you can see that there is actually a number of invalid lines within the files, and you can just you can just see what's going on there. And you see that the import has been finished actually. So let's see if there is, and actually there is something in the database. We can count the records. Well, counting is not an optimal query, and it's like if all the lines were valid, it should be 50,000. Here, some of the lines were invalid, so we have a little bit less than 50,000, and the data is there. Okay, so that's all the code I had. Of course, well, there is more. I've showed you basically how to use the built-in stages. I've showed you a bit of how to build your own flow, but you can also there is also still a more complicated DSL for writing the flows. Actually, I forgot to show one more thing, which is the Scala DSL. So here, when connecting all the stuff, we needed to use the builder. If we use the Scala DSL, we have the magic arrow operator, which basically does all the things that we do manually. It calls builder add, and it connects the inputs. So this is the place where the Java DSL, Java API for Akka Streams is not that good. I mean, in Scala it is much better. The previous API, all the other APIs are pretty much similar. So in Java 8 with lambdas, with method references, it's fairly easy and fairly comfortable to write it. But this is the place where the Scala API is more comfortable because of the magic arrows that you can use. You can build your own flow. I wrote a blog post about it and actually contributed the flow to Akka Streams contrib, so you can just read the blog post. It's written in Scala, but as I said, the API is pretty similar, so I'm more than certain that you're going to understand it even if you haven't seen Scala before. And that's it. So the QR code leads to the link that is below, so you don't need to scan it. There's a landing page at the link with links to GitHub, to the blog post, so you can find everything there. If you have any questions, I think we don't have time now, so just please catch me later if you wish, or after the conference. We can also talk about remote work if you wish. Thank you for your attention.